Now let me discuss about something called the bias trick. So in this CS231N website, and then if you click this course notes, and then there are some detailed lecture slide about the class material or the video lectures. And among them, if you click this linear classification one, and then this is mainly about lecture 2 and 3. And in this class material, there is something called this bias trick. Okay, so I will discuss a little bit more about it. And so this is about this fully connected layers. Okay, which is the one of the most basic layer, and it usually involves this bias term. Okay, and also it is called the affine layer that way. So if we see this kind of thing, y equals ax or y equals maybe ax, where a is a matrix and x is a vector. So for example, so if we have these 4 pixels for our given images, and then it will comprise or the input layer as this 4-dimensional vector. And then suppose we want to obtain this 3-dimensional vector as an output in this layer, and then this vector x will be like this, okay, as a column vector, and then the linear transformation as a matrix multiplication that will define this layer is represented as this 3 by 4 matrix, right? And that way we will obtain like 3-dimensional vector as an output. But usually we involve this bias term, okay? So the bias term is like this additional 3-dimensional vector, which is just composed of this constant value regardless of the input vector, okay? And then we add this bias vector to this resulting linear transformation vector result from this matrix and its product with the input vector, okay? So it's like if we had just a single node and then single input node and single output node, and then if we don't involve any bias terms, and then suppose we have a weight as 3, okay? So in this case, y will be equal to 3x, or in general like ax. But so this is an input one, and then in the case, this is called the linear layer, okay? But we usually involve some bias. So for example, if we want to define our layer as 3 times x plus 2, and then we usually add one as additional input node, which contains this constant value, and then we add, we define the edge weight as 2, which is coming from this bias, okay? So in this case, it is called the affine layer. So so this constant term and its addition to this linear layer is called affine layer. And in the case of this vector as an input and another vector as an output, and then bias term will be the vector that has the same dimension as this output. Okay, and then here is a bias trick. And so so in this case, 3x plus 2 can also be represented as this. So in this case, now let's think of this 2-dimensional input, okay? And then our original input value x, and then another input which is constant value as 1, and then our input vector is defined now as 2-dimensional vector instead of just a 1-dimensional value, okay? And then what is our output dimension? Output dimension is 1 because we have just a single node here, right? And then what is our linear transformation matrix and its size? And then in order to obtain just a single scalar value, and then our matrix should be 1 by 2. Okay, and then what is the coefficient? It should be 3 and 2, right? So that way, this 3 times x plus 2, which involves this additional bias or constant term, can be always converted into this matrix and vector multiplication, where this vector, right? This vector, is one more dimensional vector from the original input value, and then one more dimension always has the value as 1. Okay, so let's apply this into this vector to vector transformation case. Okay, so we have this transformation and this vector, and then additional bias term. And if you saw this 4 different perspectives of this matrix multiplication, I mean, how we understand the matrix multiplication, I mean, matrix multiplication can be categorized into 4 different categories, and one of them is like this. So we have those 4 columns in the matrix on the left, and then we have coefficients contained in the vector on the right. Okay, and then this matrix and the vector multiplication can be represented as, okay, so this vector and this vector and this vector and this vector, and then those green ones, I mean those linear combination coefficients, will work as those scaling vector of each of these column vectors that we are given. Okay, and then you will see easily this result is the same as this matrix vector multiplication. Okay, and then now we view this bias term as another column vector that is scaled, I mean that is multiplied with the scaling value as 1. Okay, scalar value as 1. And then now we have these 4 different column vectors, and so these 5 different column vectors and 5 different scalar values. Okay, so now we can view it as a linear combination of these 5 different columns, and then now we can rearrange it into matrix vector multiplication form. So now so those vectors are collected as columns of our matrix on the left. Okay, and then now those values will form a single column vector that is multiplied on the right. Okay, so okay, so back to this form. So this was our original input vector that represents our original pixel values in the case of 2 by 2 images. And now in order to involve this bias term, okay, we added one more dimension. Okay, one more dimension, and then its value is always set as 1. Okay, and then see, so this part is corresponding to the original input pixel values, and then the last column, okay, last column is representing our bias vector. Okay, oops, so here there is a typo here, so this shouldn't be 2, 1 and negative 1. Let's say 1.1, 3.2 and negative 1.2, and those values should be this vector. Okay, so that is the bias term, and then in this node link diagram is equivalent to having this one additional node which contains a constant value as 1.